Hi, this lecture is on properties of determinants. As you may remember, determinant is an operator defined on a vector space of square matrices. So the input of this operator has to be a square matrix, and a matrix that has the same number of rows as the number of columns. And the output of the operator determinant is a complex number. So it turns out that we've learned how to compute the determinant of an n by n matrix, a matrix with n rows and n columns, and we have learned to do so by defining the cofactors and the minors of this calculation, and learning that along the way there are certain properties of this operator. For example, the definition of the determinant of a matrix can be in terms of expanding, what we said, expanding over a row or expanding over a column. And by doing this expansion, we're defining the determinant as a linear combination of the cofactors. So in that calculation, if some of the entries on the row or the column that we select are 0, then that simplifies the calculation. And one of the things we learned was that if there is a row of zeros or a column of zeros, then the determinant would be 0. So there are more properties which we discuss over the next few minutes. One of the first properties we introduce here has to do with considering two matrices that are row equivalent. In other words, let's say that we consider a matrix B, which is obtained by swapping rows from a starting matrix A. So if we swap those rows, we could also consider swapping columns, something that we're less accustomed to, since swapping rows is one of the elementary row operations we learned back in the day when we discussed reduced row echelon form. But it would, in terms of the property of this property of determinants, swapping two columns would have the same effect as swapping two rows, and that effect is that the determinant of the new matrix, so here B denotes the new matrix obtained from the matrix A, and so the determinant of the new matrix is a multiple of the determinant of the original matrix A, and this would be a multiple here with number -1, so it is -1 in front. You can think of this as like multiplying determinant of A by -1. So it's no other thing that multiply determinant of A by -1. That would be the determinant of the new matrix. So here's an example. Here's a matrix with here's a matrix where n equals 4. Okay, so here number of rows and columns equals 4, and we're going to consider the following. We're going to define now a matrix A sub 1, which is obtained by swapping rows 1 and 2. Okay, so the new matrix is called A sub 1, and we're going to write the following. So remember here, the matrix A is this matrix, and so we're going to write that the determinant of the original matrix, determinant of matrix A, is equal to the determinant of the new matrix A1. Okay, so here's A1, and the determinant of that new matrix multiplied by -1 is exactly equal to the determinant of the original matrix. In the spirit of the first theorem that we learned. Okay, so we will continue with applying row operations to this original matrix, and we're going to learn a couple of new theorems, and we will illustrate each of them. So the next property also refers to an operation that's very common, especially in row reduction, and it has to do with multiples. Okay, multiples of either rows or columns. Again, we're more accustomed here to working on applying some of these operations to the rows, but the same applies or can be said about for columns. So if we have an original matrix A and we obtain a matrix B by multiplying a row of the original matrix by scalar, here alpha assumed to be a complex number, or multiplying a column by this alpha scalar, then we would say that the determinant of the new matrix is the determinant of the original matrix times that scalar we're multiplying by one row or one column of the original matrix. Okay, so let's see an application of this. So before we continue reviewing some illustrations of these theorems, let's introduce another one. Okay, so we've learned about swapping rows and the effect that has on the determinant of the new matrix. We just discussed about multiplying a row or column by scalar. And now what happens if we combine yet the multiple of a row or column with addition? So and this is the type of operation that is very common in RREF and row reduction. So suppose again that B is the new matrix and that now we're multiplying a row by a scalar alpha, right? So in both of these theorems, alpha is assumed to be a complex number in general, and then we add that to another row. Then we find that the determinant of the new matrix, of the matrix B, is exactly the same as the determinant of the original matrix A. Okay, so let's see how this is illustrated. So we come back to this example of this 4x4 matrix. We had already applied a row operation, and we generated, we went from A into A1, and now let's transform A1 into a new matrix, which we call A sub 2, by means of multiplying the row by scalar and then adding that row to another row. Right, so this gives rise to the matrix A2, which is expressed here. I'm using these two bars here to separate two things because we had previously started by saying determinant of A equals to the negative of the determinant of A1 because of the first theorem that we learned. And now what we're doing is following up here with a chain of equal signs. So how is this being the starting matrix A sub 1, how is that related to A sub 2, the new matrix? So since the last theorem tells us that this type of operation, something that looks like alpha r sub I plus r sub j, when this is what gives rise to the new matrix, then we have what we have here is that determinant of A1 is exactly equal to the determinant of A2. And for that reason, the negative stays as is. And so what we have is the determinant of the original matrix equals minus determinant of A1, which itself is equal to minus determinant of A sub 2. So now we generate yet another matrix A sub 3, which also results from multiplying a row by scalar and adding that to another row. And then I'm separating these calculations here with this line. And then we would say that the determinant of A3 is exactly equal to the determinant of A sub 2. So right, remember that we have determinant of A equals minus determinant of A1, and that would be equal to minus determinant of A2. And now we have a new matrix A sub 3, and what's going on in between there is, maybe I write this in parentheses here, is that determinant of A sub 3 is exactly equal to the determinant of A sub 2, right, by property we listed before. Therefore, right, this equal sign is now connected to this one. So determinant of A2 equals determinant of A3. We're still preserving that negative sign, and really what happens there is that determinant of A, the original matrix, is equal to minus the determinant of A3. And we can do the same type of operation a couple of times and generate A sub 4, A sub 4 here being generated from A sub 3, and also A sub 5 being generated from A sub 4. And so you see how the type of row operation we're doing, multiplying by scalar. We multiply a row by scalar and then add that to another row. We do that a couple of times, and then the same property applies, right? So we are aware that determinant of A4 is equal to determinant of A sub 3. And also, this would be something that's what allows to have these two things being equal. We're respecting there the equal sign. And also, since the same type of operation applies from A4 to A5, then we have the determinant of A sub 4 is equal to the determinant of A sub 5. And then, therefore, this continues here. So basically, what we are specifying, we have to remember that up to the top here we have a good memory. So this is coming from saying that determinant of the original matrix A is equal to minus determinant of A3, which then now we're concluding the determinant of A is temporarily equal to minus determinant of A sub 5. And look at what we have managed to do is A sub 5 is a matrix that is row equivalent to the original matrix A, such that the first column, right, the first column contains a leading one, right? So now we have converted the first column of A into a pivot column. There's a leading one position, row 1, column 1. And so what we do next is that we transform A sub 5 into A sub 6 by multiplying the second row times the scalar negative 1/2. And in doing so, we are now going to apply one of the theorems. So here the theorem that we apply is the theorem that tells us that when we multiply a row or a column by scalar, the determinant of the new matrix is simply the determinant of the original matrix times that scalar we're using to multiply the entire row or the entire column. So that theorem tells us that the determinant of the new matrix, determinant of A6, is equal to the scalar we're multiplying by a row of the previous matrix. In this case, the scalar is negative 1/2. We multiply the scalar times the determinant of the previous matrix. And so this gives us a relationship between the determinant of A sub 5 and the determinant of A sub 6. And from here, we can easily see that we can solve for determinant of A5. So we see that we can multiply by negative 2, and we have minus 2 times determinant of A sub 6 being equal to determinant of A sub 5, right? So now we have an expression for determinant of A sub 5, which is precisely what we have here. Remember, this is the chain of equal signs. This is something that keeps following from the original calculation of determinant of A, how the determinant of the original matrix relates to each and every single one of these row equivalent matrices. So now we can replace determinant of A5 by this expression, and we would have minus 2 times determinant of A6, and therefore we obtain the following equivalence in this chain of equivalent statements.